Eyes is all right. So too bad my board's not working. Um, so yeah, we're gonna just pick it up where we left off yesterday. So I'm gonna bring in a graph and then I'm gonna get rid of this. I probably shouldn't be recording all this, just me playing around here, but I'm gonna move some stuff around and I'm gonna clone this page a bunch of times. Here, now I got a bunch of clean slates here to work with. So yesterday I showed you how to graph just generally the family y equals x squared. We talked about y equals x cubed. We talked about the square root and the cube root. So we have three left to talk about. Let's do the easiest one first. It is y equals or f of x equals whatever, just the absolute value of x. If it weren't coming up in your assignment, I wouldn't even teach you this one, quite frankly, just for whatever that's worth. But it's there, so I don't, when you see it, I want you to be comfortable with what it is. Same thing as I said yesterday, rather than just show you what it looks like. Um, it's the whole teach a man to fish thing. Let's make a table. If you make a table, then you understand better where a graph comes from, right? So give me an x.
One.
I'll take one. And if you put one in, what is the absolute value of one? Correct. Give me another
Negative
X.
7.
I love negatives. I like that you just shot away from being so close to the origin. Solid. Good teamwork there, boys. What is the absolute value of -7?
7.
+7. This is going to feel very quadratic-y in the way that it conquers negativity. Like that's what x squared does is it takes a negative and like says, you shall not remain negative, right? And that's what an absolute value does too. So like if I put in 4, it's going to give me back a 4. If I put in -8, it's going to give me back an 8. And
Negative.
we do want the centering point. So I think it's important to always acknowledge what we call a vertex.
Say,
Mhm.
stop first.
Of course I can.
So I wrote down four numbers totally before you started saying this.
You wrote down the exact same numbers.
One, -7, four, negative.
Sutter, I think
He's a
that
magician.
I'm a little creeped out by that. I'm not going to lie.
I don't know what was happening.
The probability of that is, I'm not going to say astronomically because that would be a bit hyperbolic, but very low.
Maybe he's a psychic.
Maybe.
I think that you and I should pool our powers and just each of us should write down what we think this week's winning Powerball numbers are going to be. And then we can come up with some sort of algorithm to tinker and modify with what we decide on. And then we make bank and we go buy an island somewhere. All right. So I couldn't figure out why you were so animatedly interrupting me, but you're not wrong. That's creepy, dude. So 0. The 0, 0 is important because he is the vertex. Just like a parabola has like a hinging point, an absolute value graph has one as well. The difference is that this one does not have exponential arms. It doesn't grow at an increasing rate. These arms are what we call linear. So if we go through and plot all the points real quick, here's 0, 0. Here's 1, 1. Here's -7, 7, I think. Here's 4, 4. And here's -8, 8. And here's, well, I could kind of go like all day, right? But that's enough. It's the power of making a table is that a graph will just poof start to appear before your eyes when you plot enough points. So having said that, the graph of an absolute value function looks like this. It looks like a V. We come to call them V graphs.
Yes.
And as with all the other graphs we're going to do, it is modifiable. It is transformable, we say. And the word transform means you can flip it over, you can make it skinnier, you can make it fatter, you can move it left, right, up, down. There's all sorts of fun things you can do with graphs. But what I'm giving you yesterday and today so far is just what we call the parent functions. So that's the parent for the absolute value family. Next up are my two, probably they're the coolest, but they're probably my least favorite just because I think they're the most awkward and difficult to graph. So the first one is this y equals 2 to the x. This is the parent of a family that we call exponentials. And, people I used to struggle with this when I was a kid. People would say like, well, why is X squared? And I used a word earlier that I probably shouldn't have lazily thrown in. People say, why isn't it like X squared an exponential? Just because something has an exponent doesn't mean it's exponential. What does it mean to be exponential? What is my exponent? It's my variable. So let's understand that the definition of an exponential function is not x squared. That's called a power function. Exponential is when the variable is in the exponent. So this family is called exponentials. And again, we're going to make a table. So I'm going to make x and y. And again, your input is welcome, but be aware of what you're saying and don't give me something like 5, because 2 to the 5th is 32, and I'd really rather not have to modify my spacing. So 2's great. 2's a great place to start. And I like what you said also. So 2 and 3 can be my first ones. I like those both. So if you put in 2, what's 2 to the 2th? Or what's 2 to the 3rd? 8. And even 4 is going to shoot us up the grid. So let's backtrack and head the other way. 1 and 0 are both excellent inputs. What is 2 to the 1th?
2.
And what's 2 to the 0th?
0.
It is not.
Yeah.
That's one of those obscure facts that just comes up every once in a while in math, and about the time you get it, then you forget it, and then you get it, and then you forget it. At some point, just get it stuck in your head. Anything with a power of 0 just equals 1. All right. But we can also now do negatives. And so the domain of this function is not restricted like the square root was. So let's say we did like -1. I'm not going to be offended if you can't answer this, but I will be impressed and proud if you can. What is 2 to the power of -1? Good for you, Brenna. Most impressive. Remember that negative exponents don't cause things to change signs. They cause things to become fractions. So this opens up a whole new side of this curve. If I head down deeper, what's -2? It's 1/4.
Yeah.
So you see, I'm like exponentially increasing the size of the bottom of my fraction because the power of the bottom keeps getting bigger. And I could keep going, but I'll just do one more. But this can go forever. And this will be my first opportunity to use with you guys a word that I'm going to use about 1,700 more times. But I'll mention that in a minute. What's -3 going to be? 1/8. And again, I could go forever. Like if I did like -5, I could do 1/32. At this point, it's just obnoxious. And you'll find that it's hard to graph beyond a certain point because we're approaching a line that we can't see. So for the first time, I'm going to use my analogy about a plane that's trying to land that can never land. But I'll get there in a second. So let's plot the simple points first. Let's start over here on the beefier end of the table. The 0.24 is right 2 up 4, so you can knock that one out. And I know you're probably just having to sketch these, and I'm sorry for that. The 0.38 is right 3 up 6, 7, 8. And you know that the next one would be 416, right? And the next one after that would be 532 and then 664. And so it grows crazy fast. But there's some that I can like get my fingers on. And so if I do 1, I get 2. And then I'm going to cross the y-axis now. My y-intercept by definition is wherever x equals 0. That is the definition of a y-intercept. So 0, 1, this point right here is a y-intercept. This is where, for the first time ever, you're going to see the graph approaching something. Get used to this word because you're going to say it. I'm going to say it probably more than you, but between us collectively, we're going to say it about 96,000 times in the next month. The word is asymptote. The P is kind of silent. And for the first time ever, you get to see what we call asymptotic behavior. So this graph, you would agree that even if you put a huge number in place of x, I'm sorry, a big negative number like -50, -500, something like that. I don't know, you could do like -6, 7, 67, something like that. You would agree that no matter how obnoxious you get with your power of x, 2 to the -5 millionth power, it's still 1 over a number, isn't it? Does it ever reach 0? There you go. So this is your first kind of look at what we call asymptotic behavior. We say that this graph is approaching the x-axis, wait for it, asymptotically. And so these are where the graphs are really hard to graph because now I'm going to zoom in. I have an advantage over you. I can use my technology to do stuff like this. But if you look at your table, you would agree that at -1, we were at a half, right? And when at -2, we were at a fourth. And now you're seeing asymptotic behavior. When we were at -3, we were at 1/8. When you were at -4, we didn't write it down, but it would have been 1/16. It becomes very difficult to differentiate between touching the line and not touching the line. And you will find no matter how many hundreds of these you do, graphing them is difficult. Unless you've got a really good, steady, artistic hand, it's hard. And you'll find yourself erasing a lot because you're not going to settle for terrible, ugly graphs. You're going to go, that looks like garbage. I'm going to erase it and try again. And that's okay. So asymptotically, this graph will go now. And this is my analogy. It's a plane trying to land, but literally flies forever. And it keeps getting closer to the runway, which is so hard to think about, but it never touches the runway. That's nuts. But that's what that asymptotic behavior is all about. So I'm going to zoom back out now and just try to make a sketch. So your sketch would look something like this, and it basically almost mirrors, and I apologize. This would be better if I were just using a pencil on a piece of paper. So feel free to make fun of me. I don't mind one bit, but it's that asymptotic part it's for all intents and purposes, it just should look horizontal. And then it starts to grow. And there is no asymptote on the right because the graph can keep going to the right. It's not approaching anything to the right. Like you could put in 50 for X and you got no issues over there. The issue becomes, and this branches us or connects us into calculus, is this idea of a limit. In math, things have limits. They have things that they try to get to, but they can't get to. And this graph is so trying to get down to 0, it just can't, no matter how hard we try. So that is the parent function for exponentials. And again, we can do all sorts of things with it at a later date. We can stretch it. We can stretch it sideways. We can stretch it up and down. We can move it left, down. We can flip it upside down. There's all sorts of transformations that we can do. One more. Do you know who's missing by chance? If you know this or not. I don't know why you would think this, but there's one more.
Logarithmically.
Good for you. The last family that we have to talk about in this class is logs. And so the parent function is y equals log of x. What's the base of that log? 10, right. And I honestly, I probably should have Googled this before I came in here like I knew what I was talking about. I'm pretty sure log base 10 is the parent function. Maybe it's log base 2. I don't even know. Like let's Google this when I'm done yapping. But as long as you know how to graph log of x, then you'll understand from this part of the lesson how to graph log base 2, log base 3, log base 4. Like it doesn't matter. So same idea, we're going to make a table. This table is not a free-for-all. This is not just a pick a number that you feel in love with and say it, because we have to be aware of how logs work. So having said that, let's take a good close look. I'm going to go to a new page, a page without a graph on it, and we're going to study this graph, this function, log base 10 of x. Can someone give me a value of x that will not suck?
2.
2 sucks.
100.
100 does not suck. The only reason it kind of sucks is because I can't fit it on my graph, but kudos to you, because the fact that you said that tells me that you understand that a logarithm is, I'm dealing with powers of something, right? And so we understand that if we put a 100 there, so I'm going to do what Zach said, I'm going to put 100 there and it's going to say log base 10 of 100. And I don't expect you to retain everything I've ever said to you, but if you really know your logs inside out, you know right away that the answer to that problem is 2. Because what does log base 10 of 100 mean? What does it mean?
It's like how many times that bottom number. So
I love it. And I love using casual English. It's like how many times that bottom number has to multiply by itself. Couldn't have said it better myself. So when I evaluate a logarithm, I'm finding an exponent, basically. The y is the exponent required on the little baby guy to make the argument guy, right? So that's why log base 100, if I feed this function a 100, it gives me back a 2.
So we'd rather do 10 so we can actually.
So we'd rather do 10 so that we can fit it on our graph. And we can dork around with this because I don't have a lot of structured have to get dones for the day. So we can dork around a little bit more after this one. But yeah, in this case, I definitely want to use 10 because 10's the power of 10, right? So if I did log base 10 of 10, what do I get? One. What's another good one? 1,000 is great again, but not really practical. I mean, it is. And if you ever, there's almost no chance you've ever seen this, but like your dad, I bet has some laying around. You can find stuff called logarithmic graph paper. And like I say, you should ask him and see if you can find a piece of it because logarithmic graph paper takes and it allows a curve that should be invisibly far away. And the axes play with logarithms, like the powers of 10 get condensed and crunched to the point where something that should be obnoxiously like spaced out for miles fits on a piece. So hang on. I'm just going to do it. I'm recording. So just, check this out. I was looking up how to clear my queue on Spotify. So sorry for that search there. Logarithmic graph paper. Okay, that was quite a letdown. All right, that's lame. What's that? Oh, I thought you were going to say logarithmic graph paper is a song by Radiohead. And I was like, there is no way that that's true.
Well, they do have a song.
They do have
That is a bald-faced lie.
I would doubt it.
All right, so I don't waste time in this. Let me wait and I'll find a good example for you. But anyways, if you ever see logarithmic graph paper, okay, I got to look at this one. I got to dork it out because this one's awesome. Look at this. Okay, never mind. It's not there. Okay. Oh, there. Thank you. So this is logarithmic. So things that would normally curve and go obnoxious do not. Okay, this example sucks. I'm done. I give up. I'll show you one in a little bit. Anyways, logarithmic graph paper exists for a reason. Science people love that stuff. So, all right. Anyways, 1,000 is super awesome. It just isn't practical on normal graph paper. But what would it be? It takes 3 tens to make 1,000, right? So let's go in another direction. I love -10. And I'm going to leave a little space there because you forgot something really important, but it's okay. 0 will not work. What is -10? No, it doesn't work either. No, lied. There's only one more really practical one. What is it?
1.
Yeah, 1. Logs can't have negative arguments, but one works because if I say to you, what's log base 10 of 1? What is the answer? Yes, we always ask ourselves in the water cycle, 10 to what power makes 1? And the answer is 0. So the reality of our situation is that we're really only going to be able to grab these 2 points. So, but we could do another one after this with like a log base 2. And then we could fit more junk on it. But the point is, let's go take a look at what the graph looks like. And he's going to look like an exponential. But do you know what logs and exponentials are? What are they called? They're inverses. And so the graph you just saw of an exponential that shot up like this. Oh, that's not supposed to go backwards. Like this. And the graph of your exponential are going to reflect around this line. Isn't that amazing? You may not find that nearly as exciting as I do, but this graph will then curve and go this way. And I know you're probably mocking me right now, but the point is that you can expect a logarithmic curve to look like that because it's the inverse of a exponential curve. Math is a wonderful thing. All right, let's get to it. So back to this page, we already made the table, so I don't need this anymore, but I guess I could write our numbers in. We said that log base, our log of 10 is 1. We said log of 1 is 0. By the way, you can do fractions, by the way. You ready for this one? What's log of 1/10? No. What'd you say? Yes. What's log of 1/100th? Amazing. So we are going to see more asymptotic behavior. And I'm going to go ahead, I'll zoom in here after a little bit. So the first point that we all want to graph is 10, 1. So we're going to go right 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1. Don't you start with me, hockey. And then I'm going to go to 1, 0, which is right 1, up 0. And this is where I'm going to start zooming in now. So you guys keep track of these numbers over here because they're about to go bye-bye on my TV. So if I were to go right 1/10 of the way, I'm at -1, right? And if I were to go right 1/100th of the way, so there's that asymptotic behavior again. Could I have an X value of 1/1,000,000th?
Yeah.
Sure. What would the Y value be?
6 or 7.
-6, 7, something like that, right? Yes.
Yeah.
So I didn't do that on purpose, by the way. Just for the record, I should have picked a different number. Like, never mind. Yeah, so there it is. There's your asymptotic behavior. So in the same way that our exponential curve behaved asymptotically on the horizontal, this one behaves asymptotically in the vertical. And again, my friends, I wish you luck as you endeavor to make these curves, because years of experience will only lead you to the conclusion that it doesn't get any easier. The way I do it is I try to mimic the axis that it's asymptotic with. But what's tough about these guys is how sharp they kick. So this one just kicks immediately hard, almost purely horizontal like that.
That's an example. Not that example.
And I have decided that this was probably not what I should have done as the parent function, because to truly be the inverse of the last one, what base would I have had to use? Yeah, so really, if I had this last 10 minutes to do over with you, I would have picked log base 2 of X. So let's take just one quick second and do that. So help me out here. Get out of there, fat pen. You know, skinny pen. Oh, skinny pen.
What about really thick pen?
So let's do Y equals log base 2 of X. I should have done this in the first place. I don't know why I didn't catch myself, but we're better now. So give me a good X.
2.
I like 2. What is his output?
2.
Good job. Give me another good input.
4.
I like 4. What's his output?
2.
Give me another good one.
8.
What's his output? Good. And let's avoid now saying 16 because we're going to go off the graph, right? So let's go the other direction. What's the next good input?
1.5.
1.
Thank you. And what's his output?
Mhm.
0. And now this time I'm not going to be saying things like 1/10 and 1/100th. What's my first good fractional input? 1/2. And then my next one is like 1/4. And those are going to be -1 and -2, right? So this one you will truly see is the inverse of the one that we did. So I would think that I should have used this and called this the parent function. I apologize for that. Let's take a look. So make some graphy points. So 2, 1 is right here. 4, 2 is right here. 8, 3, 6, 8 is right here. And then we have 1, 0. And this is where he starts his asymptotic approach towards the y-axis. If you don't stop clicking that pen, you and I are going to have a rough finish to our afternoon. Yeah, he knows. So if I go right a half of the way, I'm at -1. And if I go right a quarter of the way, I'm at -2. And then if I go right an eighth of the way, I am at -3 and so on. So this is a much more comfortable situation. That 1/10 was pretty dang sharp, but this one is a little slicker. So you can, again, mimic the axis to which it's asymptotic and then smooth curve. Plan to do, again, lots and lots of erasing. That actually went better than I thought it would. So got it. Those are the families of functions. And now what I want to talk to you about is how to do transformations. And so this should not take too long. And you don't have to graph anything by hand today. Like I said, Delta Math will graph it and you just move it. So here is what it's going to look like. I'll try to do a couple of examples to not pile on here. So, and you, by the way, you've seen this before with quadratics. There's almost zero chance you'll remember this conversation, but you have done transformations in my class before when we graphed parabolas. So here it goes. Let's say I did y equals x minus 4 squared plus 3. First off, what family is he? What family? X squared. So we know we identify a picture in our mind of what the parent function looks like, and we rest assured that no matter how I play with it and I add numbers in different places, it's still going to be a parabola. Right. So does anyone by chance remember from our past together what the -4 does to the graph? Go ahead.
It makes it go to the right.
Yeah, I'm impressed that you remember that. It makes this graph actually go to the right 4. You guys remember what the +3 does?
Yeah.
It goes up 3. And that's where it's like almost like someone's messing with your brain. Is like the inside one, and this makes more sense as you get older and older and older, that the inside one, it's not like voodoo, like some guy in a cave with a long beard trying to trick young people. The reason we go backwards is because we're trying to center. We're trying to find symmetry at the vertex. So when you make something equal 0 horizontally, then you've found symmetry. And the number that makes the center is the +4. So it's not witchcraft. We don't change the sign because of witchcraft. We're trying to make center. And then the 3 is just an afterthought vertical motion. So what I would do on this one is I would understand what it is, and then I would just take the graph, the parent function, and I could just consider 1 point on the graph enough. There's where the parent dot would be, but I'm going to move the graph where? I'm going to go right 4 and up 3. And I didn't mean to grab the whole graph, so that's not going to work. So I'm going to go right 1, 2, 3, 4, up 1, 2, 3. And I'm just going to, I'm going to rebuild there. Right? My blueprints are the same. I'm just going to go to a new place. And then from here, I would just rebuild the parent function. And what is the relationship? How am I going to build those extra points on the outside? You bet. So there's the purple points are going to be my guys. 1, 4, 9. Is this ringing some bells?
Yeah.
So on delta, it's going to be pretty slick. It'll have a point, usually like the center, the hinge point. In this case, the vertex, you can actually grab it, drag it, place it, submit it. It's a great introductory way to do transformations. Let's try another transformation. How about y equals the negative of the absolute value of x minus 2? How many transformations do you see? 2. Transformation just means change. One change is the -2 at the back that's going to cause it to go down 2. Quit throwing gang signs at me. And then the negative on the front means, I know, I'm just giving you grief. I like to say stupid things. The life gets too boring if you don't say stupid things every once in a while. And for me, that means like 40 times a day. So yes, the -2 is a vertical 2, and then the negative in the front is a flipper. So again, I just think about where parent function home base would be. It'd be right here in the middle. And I'm like, okay, I'm just going to move you and rebuild you. So I'm going to go down 2, and there's my new hinge. And because the negative is on the X, I'm just going to build the same exact graph upside down like this. Got it? How about, I'm running out of, I thought I had plenty. Oh, I do have plenty. Look at me. How about this one? How about y equals the cube root of x plus 3 minus 1?
That's the thing.
Your job here is first off to immediately recall what it looks like, right? You remember he's sideways snaky? Okay. So again, there's a different lesson that is not today's lesson where I will show you how to actually physically reconstruct the whole graph. Okay. But for today, really all you're going to have to do is grab a single point on it and move it. So where does this graph go? It'll go to the left, 1, 2, 3, and where else?
Down.
So 1, 2, 3, down 1. And then the graph will reconstruct itself at that point. And the reconstruction is the 1, 1. And then I think it's like, I don't think I went 1, 2, 3, 4, 5, 6. Okay, never, I don't know why. It's right here. And then there's another one right here. And then there's another one like way over here or something like that. But that's the gist of this, is that you're building the same things. You're just basically building them in different locations. My apologies. That's one of the worst graphs you'll ever see. FYI. You're welcome. I'll take a picture of that and sign copies of it for you. So here we go. Let's take a look at the old delta math before I shut up, so you can see what you're up against here. Oh, and by the way, there's also some where you have to write the equation given the function. I kind of forgot to mention that. Show. Let's do a new problem. Got it? You see the graph? Watch how easy this is. Where am I going to move this graph? Right. So I'm just going to grab the graph. Math doesn't get much more user-friendly than this. I'm going to grab this green dot and I'm going to move it left 1 and down 1, 2, 3. I'm going to reposition it. And I'm going to
grab the dots.
The blue dots are when we have to start doing these. And I don't know if those are going to be in here, but we're about to find out. So we're going to send that one. Let's do another one. How about this one?
So you go left 5.
Left 5 up 4. And again, you can just grab green dot. The blue dots are for resizing and reorienting the graph. The green is just for moving the home base. So let's see if we can find something more challenging. That's lame. How about this one?
Left 5.
Right
No,
5.
Yeah.
Up 4. So 1, 2, 3, 4, 5, 1, 2, 3, 4. This is a good sort of almost childishly simple way to introduce yourself to the idea of moving things around. But again, I don't seem to see any. Oh, rats, there was a good one. How about this one? Where does he go?
Just left 5.
Eh,
Oh, no, just down.
down 5, right? So I'm going to grab this point and move it down 1, 2, 3, 4, 5, like this. Okay. So what I was hoping for, and I'll have to search for this. It's okay because we've got a few people gone, but what I want is for there to be some other types of numbers. So this must be like level 2. Somewhere I got to find a level 3 because I don't think based on my experience with this so far that you're ever going to have to use the blue dots, which is actually kind of lame, but there's only, say what?
The whole assignment is all.
I know, but I thought level 2 I thought it was going to be a mixed bag of left, right, and also stretchies. So apparently I was wrong. So you prepare for this to be a pretty boring endeavor. So let's knock this one out. And then tomorrow I'll be prepared with talking about the more exciting types of transformations, the flips and the stretches. Okay.
It's the great side of the shit old now.